Look up at the night sky, and you'll see stars glittering like distant diamonds, but hidden among them are some of the universe's most breathtaking and enigmatic creations, planetary nebulas. These cosmic masterpieces, glowing with vibrant hues of blue, green, and red, are far more than just pretty decorations in the void. They're the final, dazzling acts of dying stars, painting the cosmos with their last breaths. Yet behind their beauty lies a trove of mysteries that defy our expectations. Why do some of these nebulas take on bizarre, asymmetrical shapes, as if sculpted by invisible hands? How can a single star produce such intricate, almost artistic structures? And what secrets do these celestial spectacles hold about the fate of our own sun? For centuries, planetary nebulas fooled even the greatest astronomers. Their name comes from an old misconception that they resembled distant planets. Today, we know there's something far more extraordinary: the outer layers of aging stars ejected into space and illuminated by the fierce ultraviolet light of the stellar core left behind. But every time we think we've unraveled their secrets, new discoveries upend our understanding. Some nebulas spin at impossible speeds, while others harbor hidden companion stars pulling their gas into strange, twisted forms. Some even flicker like cosmic ghosts, changing shape over mere decades, a blink of an eye in astronomical terms. This is where the story gets truly fascinating. Planetary nebulas aren't just relics of stellar death. They're time capsules revealing how stars recycle their ingredients back into the universe, seeding future generations of planets and perhaps even life. Join us as we unravel 30 of the strangest, most awe-inspiring discoveries about these cosmic phantoms. From bizarre magnetic fields stronger than anything on Earth to the eerie, butterfly nebulas stretching light years across space, each revelation will leave you questioning what else lies hidden in the depths of the cosmos. The universe has a flair for the dramatic, and planetary nebulas are its grandest performance. Let's take a front-row seat. Among the countless planetary nebulas dotting the cosmos, few are as striking or as puzzling as the Butterfly Nebula. Stretching over 2 light-years across, its wings of glowing gas fan outward with near-perfect symmetry, as if some celestial artist meticulously sculpted them. But this breathtaking beauty hides a violent backstory. Most planetary nebulas form messy, irregular shapes as their dying stars shed layers unevenly. So how did the Butterfly Nebula achieve such flawless balance? The answer might lie in a cosmic dance of destruction. Astronomers suspect the central star once had a companion, locked in a gravitational tug of war. As the primary star expanded into its death throes, its outer layers spiraled toward the smaller star, which then funneled the material into twin jets, carving out the nebula's iconic wings. Another theory points to an incredibly strong magnetic field, shaping the ejected gas like invisible hands molding clay. But here's the twist. The Butterfly Nebula's core star is one of the hottest ever recorded, blazing at nearly 250,000 degrees Celsius. That intense heat combined with these mysterious forces creates a structure so precise it's almost unnatural. Even stranger, the nebula's symmetry isn't just for show. The same forces that sculpted its wings also enriched it with complex molecules, including carbon and nitrogen raw ingredients for future stars and planets. So while it looks like a fragile cosmic artwork, the Butterfly Nebula is really a furnace of creation, proving that even in death, stars leave behind the building blocks of new life. If the Butterfly Nebula left you in awe of cosmic symmetry, wait until you meet its even more baffling cousin, the Red Square Nebula. Nestled in the constellation Serpens, this structure defies everything we know about how gas and dust behave in space. While most nebulas twist into spirals or stretch into uneven clouds, this one forms a nearly perfect square, its crimson walls glowing with eerie precision. It's as if the universe tossed aside its usual chaos and drafted this nebula with a ruler and compass. So how does a dying star create such sharp geometric perfection? The leading theory involves two cones of dust ejected by the central star, aligned back to back like hourglasses. From our vantage point, we see them edge on, their rims tracing the unmistakable outline of a square. But here's the catch. This requires conditions so precise, even slight variations would crumple the shape into the usual cosmic swirls. The Red Square Nebula's crisp edges suggest something, or someone, is playing by different rules. Some astronomers speculate hidden magnetic fields or a binary star system might be sculpting the dust with unnatural control. Others point to the nebula's unusual composition. Its dust grains are larger and more uniform than typical stardust, behaving less like scattered sand and more like bricks in a wall. And then there's the color, a deep ruby red unlike the usual blues and greens of planetary nebulas, hinting at rare molecules like polycyclic aromatic hydrocarbons, the same compounds found in soot and interstellar space. But the real shocker, the Red Square Nebula isn't just a cosmic oddity, it's a time machine. Infrared observations reveal concentric rings within its structure, like tree rings marking the star's violent pulses before its final collapse. Each ring captures a moment in the star's death throes, offering a step-by-step replay of its self-destruction. For scientists, it's a gold mine, a chance to decode how stars like our Sun might one day shape their own final act. The universe loves a good mystery, and the Red Square Nebula is one of its most tantalizing puzzles. If the Red Square Nebula feels like a cosmic mystery, then the Helix Nebula, nicknamed the Eye of Sauron for its unsettling resemblance to Tolkien's all-seeing villain, takes eerie to a whole new level. Located roughly 700 light-years away in Aquarius, this vast glowing ring stares back at us with an intensity that's almost unsettling. Its deep blue center, surrounded by fiery red tendrils, looks less like a dying star and more like something watching from the void. But the real horror or wonder, depending on how you see it, isn't just its appearance. It's the fact that this nebula is a preview of our own sun's fate billions of years from now. The helix's vibrant hues come from a brutal ultraviolet onslaught. At its core lies a white dwarf, the exposed skeleton of a star that once resembled ours, now unleashing radiation so intense it lights up its own expelled gas like a neon sign. The blue glow, that's oxygen atoms stripped of electrons and forced to fluoresce under the star's merciless glare. The red outer filaments, hydrogen gas burning like embers in the cosmic wind. But the most chilling detail isn't the colors, it's how close we are. At just 700 light-years, the Helix is one of the nearest planetary nebulas to Earth, so near that early astronomers mistook it for a dying planet instead of a star's final act. And then there's the structure itself. Most nebulas balloon outward in uneven bursts, yet the Helix's rings are nearly perfect concentric circles, a ripple effect from the star shedding its skin in pulses over thousands of years. But here's where it gets weird. Those iconic eye-like tendrils aren't smooth. They're made of thousands of comet-shaped knots, each one bigger than our solar system. These strange droplets, rich in molecules that could form new planets, defy physics by surviving the white dwarf's lethal radiation. Some scientists think they're shields, dense globs of gas protecting their cores like cosmic bunkers, while others believe they're evidence of undiscovered physics, clumps that shouldn't exist under such extreme conditions. The Eye of Sauron isn't just watching us, it's teaching us. Hidden in its glow are clues about how stars like ours seed the universe with the ingredients for life long after their death. And if those icy knots hold water quite literally, they might even carry the building blocks of biology, frozen in the depths of space until they find a new home. The universe has a dark sense of humor, turning a symbol of fictional doom into a beacon of real cosmic rebirth. The Boomerang Nebula doesn't just defy expectations, it shatters them, holding a record so extreme it feels almost unnatural. Tucked away in the constellation Centaurus, this cosmic spectacle isn't just cold, It's the coldest known place in the entire universe, plunging to a staggering negative 272 degrees Celsius. That's just 1 degree warmer than absolute zero, the theoretical limit where all motion stops. To put that in perspective, even the vast, empty voids between galaxies aren't this frigid. So how does a dying star create a deep freeze in the middle of space? The answer lies in the nebula's explosive farewell. Unlike most planetary nebulas, which eject their outer layers at a steady pace, the Boomerang's central star is flinging gas outward at a mind-bending speed of over 160 kilometers per second faster than any other known nebula. This rapid expansion works like a cosmic air conditioner, chilling the gas as it races into the vacuum. Imagine opening a freezer door on Earth. The cold air rushes out because it's expanding quickly. The Boomerang Nebula does the same thing, but on a scale so massive it turns an entire region of space into an icebox. What's even wilder is the nebula's shape. True to its name, it isn't a perfect sphere or a chaotic cloud. It's a near-symmetrical bow tie of frosty gas, with two lobes stretching outward like the wings of the Butterfly Nebula's colder, darker cousin. But here's the twist: those lobes aren't just expanding, they're filled with tiny dust grains which act like microscopic refrigerants, absorbing heat and radiating it away into the void. This double whammy, ultra-fast expansion and dust-powered cooling, creates a pocket of space so cold, it defies the ambient warmth of the universe itself. And then there's the ghostly glow. Most planetary nebulas light up under ultraviolet radiation, but the Boomerang's faint shimmer comes from an entirely different source: starlight scattering off its dust particles like a cosmic fog reflecting a distant street lamp. It's so faint, in fact, that astronomers almost missed it entirely until radio telescopes revealed its true, frigid nature. But the real kicker: this nebula might be a glimpse into the far, far future. As the universe continues expanding over trillions of years, even the background temperature of space will gradually drop. The Boomerang Nebula is a preview of that ultimate cold, a chilling reminder that even in the fiery chaos of stellar death, the cosmos has a way of preserving its quietest, most frozen corners. The Southern Crab Nebula doesn't just stand out, it outright bewilders. Nicknamed for its bizarre, lobster-like claws, this cosmic anomaly looks less like a dying star's farewell and more like a deep-sea creature frozen in the depths of space. Captured in stunning detail by the Hubble Space Telescope, its pincer-shaped arms curl outward with an almost deliberate symmetry, as if some unseen force carefully arranged them. But what could possibly sculpt a nebula into such a peculiar shape? The answer lies in a celestial tango of destruction where two stars waltz too close to the edge. At the heart of the Southern Crab's drama is a binary system, an aging red giant and a white dwarf locked in a gravitational embrace. As the red giant sheds its outer layers, the white dwarf doesn't just passively orbit, it feasts. Material spirals from the dying star onto its denser companion, but not all of it gets consumed. Some gets funneled into twin jets, screaming outward at blistering speeds and carving the nebula's iconic claws. Think of it like a garden sprinkler gone rogue, with streams of gas shooting out in opposite directions, then getting twisted into intricate shapes by the star's orbital dance. Hubble's images reveal even wilder details. Those claws aren't smooth, they're studded with glowing knots and filaments, evidence of violent outbursts that happened in pulses over centuries. And here's the twist: the entire structure is nested inside a larger, older bubble of gas, a relic of an earlier eruption. It's like finding a smaller, fiercer storm brewing inside the eye of a hurricane. This layered violence suggests the binary stars have been staging this explosive performance for millennia, with each act leaving behind a new shell of glowing wreckage. But the Southern Crab's most haunting secret: it's a ticking time bomb. The white dwarf is greedily hoarding stolen material, inching closer to a catastrophic limit. If it crosses that threshold, it could detonate in a Type Ia supernova, one of the universe's most violent eruptions. For now, though, it's content to sculpt its lobster claws, a fleeting masterpiece in the cosmos's gallery of doomed art. The Mycene 18 Nebula doesn't just look like an hourglass, it's a cosmic timepiece, counting down the final moments of a dying star with eerie precision. Nicknamed the etched hourglass for its delicate, almost sculpted appearance, this nebula's symmetry is so flawless it seems impossible. Twin cones of glowing gas stretch outward, their edges razor-sharp, as if some celestial hand carved them from the darkness, but don't let its elegance fool you. This beauty is born from chaos, a testament to the brutal forces unleashed when a star exhausts its fuel and begins tearing itself apart. What makes Mycene 18 so extraordinary isn't just its shape, but how it got that way. Most planetary nebulas expand in messy, uneven bursts, their structures warped by turbulent stellar winds or the gravitational pull of companion stars. But here, the star's dying breaths were channeled into two opposing jets, streaming outward at nearly 600,000 kilometers per hour. These jets act like interstellar sandblasters, carving the surrounding gas into that iconic hourglass silhouette. The finer details, those intricate, lace-like patterns along the edges, are etched by secondary winds, slower but equally relentless, sweeping up dust and gas like a cosmic broom. Yet the real magic lies in the chemistry. The hourglow's vivid red hue comes from ionized nitrogen, a telltale sign of the star's violent past. Meanwhile, the blue-green rings at its waist are oxygen, glowing under the ultraviolet fury of the exposed stellar core. This isn't just a dying star's funeral shroud. It's a layered masterpiece, each element a brushstroke revealing a different chapter of its demise. And then there's the twist. Hubble's close-up images reveal tiny knots embedded in the gas, dense clumps of material resisting the stellar wind's relentless push. These knots shouldn't survive such extreme conditions, yet there they are, stubbornly holding their ground like rocks in a hurricane. Some scientists think they're the seeds of future comets or planets, forged in the furnace of stellar death. Others speculate they're evidence of magnetic fields, invisible lines of force shaping the chaos into order. The etched hourglass isn't just a relic of destruction, it's a blueprint. By studying its precise structure, astronomers can decode how stars recycle their ingredients back into the universe, crafting the raw materials for new worlds. It's a reminder that even in death, stars don't just vanish, they leave behind a legacy written in light and gas, a message etched across the cosmos for anyone brave enough to look. Some cosmic formations feel almost deliberate, as if the universe itself decided to leave a signature, and few are as hauntingly precise as the so-called Hand of God. Stretching its luminous fingers across 150 light-years of space, this nebula, officially catalogued as PSRB 15958, looks less like a random cloud and more like a skeletal hand reaching through the void. But what makes this ghostly structure even stranger is the fact that it's not just a dead star's remnant, it's a pulsar's handiwork, shaped by forces so powerful they bend physics to their will. At the heart of this celestial phantom lies a rapidly spinning neutron star, a pulsar so energetic it rotates 7 times every second, spewing out charged particles at nearly the speed of light. These particles collide with surrounding gas, energizing it until it glows an eerie blue in X-ray observations, tracing out those unmistakable finger-like tendrils. But here's the twist. Those fingers aren't just random wisps. They're sculpted by a magnetic field trillions of times stronger than Earth's, twisting the nebula into its haunting shape like an invisible potter molding clay. This magnetic grip doesn't just shape the nebula, it supercharges it. The pulsar's wind, a torrent of electrons and ions, rides these field lines like cosmic highways, funneling energy into specific regions and leaving others dark. The result, a structure so detailed, it even reveals bones within the fingers, denser threads where the magnetic field tightens its grasp. It's as if the universe took a stellar corpse and turned it into an intricate sculpture, one that pulses with energy even in death. Yet the most unsettling part isn't the hand's appearance, it's its age. The pulsar at its core is roughly 1,700 years old, a blink in cosmic terms. That means this nebula is still growing, its fingers stretching further into space with each passing century. Some projections suggest it might one day rival even the Crab Nebula in size, a testament to the raw power lurking within neutron stars. And then there's the ultimate irony: the hand of God isn't divine at all. It's the aftermath of violence, a star that collapsed so catastrophically it left behind a magnetic monster. Yet in its destruction, it created something eerily beautiful, a reminder that even in the coldest depths of space, the universe has a flair for the dramatic. Whether you see it as a celestial salute or a cosmic memento mori, one thing's certain: this ghostly hand won't let go of our curiosity anytime soon. In the cosmic jewelry box of planetary nebulas, few are as stunning or as deceptive as Able 33. Floating in the vast expanse of Hydra, this nebula's pristine, circular ring shines like a diamond-studded band, so flawless it could pass for an engagement ring slipped onto the finger of the universe itself. But here's the secret: that dazzling gem at its center isn't what it seems. The star you'd swear is nestled inside the ring. It's actually a foreground imposter, a chance alignment tricking our eyes into seeing celestial romance where none exists. The real magic of Able 33 lies in its structure. Unlike many planetary nebulas which warp into spirals or asymmetrical blobs under the chaos of stellar death, this one expanded almost perfectly evenly, leaving behind a near mathematical circle of glowing gas. The reason: a remarkably steady demise. Most dying stars cough out their outer layers in fits and starts, creating lumpy, uneven shapes. But Able 33's progenitor star exhaled its atmosphere in a slow, controlled sigh, allowing the gas to drift outward in a uniform bubble. The result is a ring so symmetrical, it rivals Saturn's, except instead of ice and rock, it's made of ionized oxygen and hydrogen, glowing electric blue under the ultraviolet glare of the hidden central star. Ah, yes, the real star. Unlike the photogenic interloper that appears to sit at the ring's heart, the actual remnant of this stellar death hides in plain sight, a faint white dwarf lurking off-center like a shy artist refusing to sign their masterpiece. That misalignment is another clue to the nebula's tranquil formation. No violent binary companion yanked it off kilter, no magnetic fields twisted it into knots. Just a star fading quietly into retirement, its outer layers peeling away like petals from a cosmic flower. But don't let its serenity fool you. Able 33's diamond ring illusion isn't just a pretty accident, it's a time capsule. The gas in that pristine ring is rich with carbon, nitrogen, and other elements forged in the star's core, now being recycled back into the galaxy and that foreground star. While it's merely a bystander, its juxtaposition offers astronomers a rare gift, a natural spotlight casting the nebula's delicate structure into sharp relief against the darkness. So next time you gaze at an engagement ring, remember, the universe has its own version, one where the gem is an optical illusion, the band is a star's final breath, and the promise isn't forever, just billions of years in the making. The Twin Jet Nebula doesn't just live up to its name, it takes cosmic drama to dizzying new heights. Officially catalogued as PNM29, this celestial spectacle flings two opposing jets of gas into space at speeds topping 1 million kilometers per hour, their spiraling paths twisting like glowing strands of DNA across the void. But what makes these outflows truly extraordinary isn't their speed, it's the stellar tango powering them. At the nebula's heart hides not one dying star, but two, locked in an orbital embrace so intimate they complete a full rotation every 120 years. This binary ballet is the engine behind the nebula's breathtaking jets. As the primary star sheds its outer layers in its death throes, its smaller companion intercepts some of that material, funneling it into twin beams along their shared axis of rotation. Picture a garden sprinkler spinning wildly, except here, the water is superheated plasma and the sprinkler is whirling at stellar velocities. The result? Those iconic corkscrew trails, each loop marking another turn in the star's gravitational waltz. Hubble's images reveal the structure in staggering detail. The jets aren't smooth streams but fragmented chains of glowing knots, like pearls on a cosmic necklace, each one a shock wave where faster-moving gas rams into slower ejecta from earlier eruptions. Yet the real surprise lies in the chemistry. The jet's emerald hue comes from ionized oxygen, but spectra reveal something far stranger: iron gas forged in the star's cores, now being blasted into interstellar space. This heavy element payload suggests the primary star wasn't just a mild-mannered sun-like star, but a more massive object that once cooked these metals in its furnace-like interior. Meanwhile, the nebula's butterfly-shaped outer lobes tell another story entirely. Their crimson glow betrays the presence of nitrogen-rich gas ejected tens of thousands of years earlier, now being lit up by the white-hot remnant stars like a cosmic crime scene frozen in time. The Twin Jet Nebula isn't just a pretty light show. Those dueling outflows act like a particle accelerator, creating conditions so extreme they generate X-rays, something rarely seen in planetary nebulas. Some theories suggest magnetic fields, amplified by the star's rapid spin, are slingshotting material outward with enough force to rival small supernova. Others propose the companion star's gravity is stripping material so efficiently, it's created a mini accretion disk hotter than the surface of our Sun. But perhaps most haunting is the nebula's inevitable fate. As the stars continue their pirouette, their orbits will gradually decay, pulling them closer over millennia until, in a final act of cosmic cannibalism, the smaller star may plunge into its partner, triggering an eruption that could outshine the nebula itself. For now, though, the Twin Jet Nebula remains a celestial whirligig, its hypnotic spirals reminding us that even in death, stars rarely bow out alone. At first glance, the TC-1 Nebula seems like just another cosmic afterglow, a dying star's final shimmer against the black velvet of space. But hidden within its gaseous folds lies a revelation so peculiar, it rewrote our understanding of chemistry beyond Earth. The soccer ball molecule, officially known as Buckminster fullerene or C60. Picture a microscopic carbon cage, 60 atoms strong, arranged in perfect pentagons and hexagons like the panels of a soccer ball. This isn't just a molecular curiosity, it's proof that the universe assembles complex organic structures in the most unexpected places. How does a dying star forge something so intricate? When sun-like stars exhaust their fuel, they don't just fade quietly, they become alchemists. In their final phases, they dredge up carbon from their cores, scattering it into space through stellar winds. But in TC-1's case, conditions were just right for these carbon atoms to link up into those iconic cage-like shapes. Think of it like a cosmic kiln, where the star's outer layers act as both furnace and assembly line, with shockwaves from the dying star providing the energy needed to weld atoms into these geometric marvels. The real kicker, C60 isn't alone. Spectroscopy reveals it's accompanied by even larger carbon cousins like C70 and C84, all forming a family of fullerenes. These molecules aren't just space oddities, they're thought to be cosmic taxis, potentially shielding fragile organic compounds as they hitchhike between stars. Some scientists speculate they could even carry the precursors to life, ferrying amino acids or other building blocks through the radiation-bathed voids of space. Then there's the nebula itself. Unlike the chaotic swirls of many planetary nebulas, TC-1's structure is eerily calm, almost as if its gentle expansion provided the perfect nursery for these delicate molecules. No violent jets or magnetic storms disrupted the process, just a steady exhale of gas, cool enough for carbon to clump, but not so cold it froze into simpler forms. It's a Goldilocks zone for molecular architecture, proving that sometimes stellar death isn't an end, it's a workshop. The discovery of C60 in TC1 does more than dazzle chemists. It blurs the line between the inorganic and the organic. If complex carbon cages can form effortlessly in the debris of dying stars, what else might be lurking out there? From interstellar alcohols to sugar molecules, each find chips away at the idea that life's ingredients are unique to Earth. The universe, it seems, has been playing cosmic Lego with carbon long before planets or life ever entered the picture. If the universe has a favorite artist, it might be the star at the heart of the Cat's Eye Nebula, because this cosmic masterpiece didn't just die, it left behind a series of glowing, concentric rings like the delicate brushstrokes of some interstellar Van Gogh. Officially catalogued as NGC 6543, this nebula isn't just another pretty face in the cosmos. Its intricate, onion-like layers tell a story of stellar death in chapters, each ring a frozen snapshot of the star's final, violent tantrums. And thanks to Hubble's razor-sharp vision, we've gotten front-row seats to decode its secrets. What makes these rings so extraordinary is their precision. Most dying stars shed their outer layers in messy, uneven bursts, creating chaotic bubbles of gas. But the Cat's Eye's progenitor star ejected its material in near-perfect, evenly spaced intervals, like a clockwork volcano erupting every 1,500 years. Each pulse sent a new shell of gas racing outward, plowing into the previous one and lighting up under the star's withering ultraviolet glare. The result: a structure so layered it resembles the cross-section of a tree, its rings marking the passage of cosmic time. Now, here's the twist. These rings aren't just relics of the star's death throes, they're evidence of a hidden companion. Astronomers suspect the dying star wasn't alone. A smaller, stealthy partner may have been orbiting close enough to gravitationally tug on its outer layers, triggering those periodic eruptions. Think of it like a stellar metronome, with the companion's dance steps dictating the rhythm of the explosions. Without it, the Cat's Eye might have been just another lopsided nebula. Instead, it's a celestial bullseye, its symmetry so uncanny it borders on artificial. Hubble's close-ups reveal even wilder details. Those iconic rings aren't smooth, they're studded with knots and braids of gas, twisted into intricate shapes by magnetic fields or shockwaves from later eruptions. And at the very center, a white dwarf so hot it blazes at 80,000 degrees Celsius, its radiation ionizing the surrounding gas into that signature electric blue and green glow. But the real showstopper is the nebula's inner structure, a chaotic web of jets and bubbles, proof that the star's final acts were anything but orderly. The Cat's Eye's concentric rings do more than dazzle, they rewrite the rules. Before Hubble, no one imagined a star could die with such rhythmic precision. Now, they're a Rosetta Stone for understanding how sun-like stars recycle their ingredients back into the cosmos. Every ring is a time capsule, packed with carbon, oxygen, and nitrogen, the raw materials for future planets and perhaps even life. So while it's nicknamed for its feline resemblance, the Cat's Eye might be better described as a cosmic fingerprint, a unique signature left by a star that refused to fade quietly into the dark. The Helix Nebula isn't just another cosmic spectacle, it's a jewel box ripped open and scattered across the void. Its glowing gas beads strung together like pearls on an invisible cosmic thread. Officially catalogued as PNG 054.2-03.4, this dazzling structure began as a celestial crime scene where one star quite literally consumed another. What we see now is the aftermath, a necklace of stellar debris, each pearl a dense knot of gas superheated to over 50,000 degrees Celsius, shimmering in the ultraviolet glare of the surviving star. At the heart of this drama lies a binary system gone wrong. Roughly 10,000 years ago, two stars, one a bloated red giant, the other a smaller, denser companion, orbited too close for comfort. As the red giant expanded in its death throes, it engulfed its partner, swallowing it whole. But the smaller star didn't vanish without a fight. Spiraling inexorably toward its larger sibling's core, it churned up the red giant's outer layers like a spoon stirring cosmic soup. This gravitational turmoil catapulted vast amounts of gas into space, while the companion's orbit whipped the ejected material into a colossal ring. Here's where the magic happens. That ring wasn't smooth. Instabilities fractured it into dozens of clumps, each one pulled inward by gravity but pushed outward by radiation pressure from the central stars. The result, a perfect balancing act, with these blobs crystallizing into the nebula's signature beads, each roughly the size of our solar system. Hubble's images reveal them in astonishing detail, iridescent spheres of oxygen, nitrogen, and hydrogen, their surfaces rippling with shockwaves as they plow through thinner interstellar gas. But the real showstopper is the nebula's center. The surviving stars, now a tight binary of a white dwarf and its erstwhile predator, still whirl around each other every 1.2 days, their furious dance ionizing the surrounding gas into a neon pink glow. This relentless radiation is what makes the pearls shine so brilliantly, their light echoing across 3,000 light years to reach us. What's chilling is how common this carnage might be. Astronomers estimate up to 20% of planetary nebulas could hide similar binary horror stories, their intricate shapes forged in the chaos of stellar cannibalism. The Helix Nebula just happens to be one of the few where the evidence is strung up for all to see, a cosmic trophy case displaying the universe's flair for turning destruction into something breathtaking. Deep in the Serpens Nebula, something lurks, not a creature of flesh and blood, but a cosmic phantom stretching its wings across the void. Known as the Bat Shadow, this eerie formation isn't a nebula or a dying star. It's an illusion, a trick of light and dust so convincing it looks like a nocturnal predator frozen mid-flight. The bat is actually the silhouette of a protoplanetary disk, a dense, pancake-shaped ring of gas and dust swirling around a young star. But here's the twist. This disk isn't just passively orbiting, it's actively sculpting its own shadow theater on a scale that dwarfs our entire solar system. The Bat Shadow's wingspan stretches an astonishing 200 times the distance from Earth to the Sun, their inky darkness contrasting sharply with the glowing nebula behind them. So how does a disk of dust cast such a dramatic shadow? The answer lies in the star's positioning. Unlike most protoplanetary disks which we see face on or edge on, this one is tilted at a precise angle like a vinyl record caught mid-spin. As light from the newborn star escapes upward and downward, it illuminates the surrounding nebula, but the disk itself blocks the light in two vast, wedge-shaped regions, creating those iconic wings. But the real magic isn't just the shadow, it's the motion. Hubble's observations reveal the wings aren't static. Over just 400 days, they appear to flap, shifting position as the disk wobbles like a spinning top. Some astronomers attribute this to a hidden planetary companion, its gravity tugging the disk off kilter. Others suspect magnetic fields, warping the disk structure like invisible hands folding paper. Either way, the effect is a celestial shadow puppet show playing out over millennia, and then there's the dust itself. Unlike the fine, powdery grains found in most disks, the Bat Shadow's material is likely clumped into pebble-sized aggregates, early building blocks of planets. These chunks are dense enough to block starlight completely, yet porous enough to let some radiation filter through, giving the wings their subtly textured appearance. It's a cosmic balancing act. Too much dust and the shadow would be pitch black, too little, and it would vanish entirely. What makes the Bat Shadow truly extraordinary is its rarity. For every 1,000 protoplanetary disks we've observed, maybe one aligns just right to cast such a vivid silhouette. It's a fleeting phase, too. As the star ages and the disk dissipates, the shadow will fade, leaving no trace of its ghostly wings. For now, though, it serves as a reminder, even in the cold vastness of space, the universe has a flair for drama, turning something as mundane as a dust disk into a masterpiece of light and shadow. The water fountain nebula doesn't just live up to its name, it defies it. Officially catalogued as ERAS 16342-3814, this cosmic anomaly isn't merely spraying water. It's launching it across space at 500,000 miles per hour, creating high-speed jets so intense they glow like celestial fire hoses. But here's the twist: that water isn't liquid. It's vaporized molecules ripped apart and reassembled in the chaos of a dying star's last act, and it's rewriting our understanding of how planetary nebulas sculpt their surroundings. At first glance, the Water Fountain Nebula looks like a cosmic inkblot, a chaotic swirl of dust and gas. But peer closer with radio telescopes, and the real spectacle emerges: twin jets of water mazes, beams of microwave radiation emitted by water molecules being whipped into frenzy. These aren't gentle streams, they're supersonic geysers, blasting outward at speeds that could cross the distance from Earth to the Moon in under 30 minutes. What could possibly power such violent outflows? The answer lies buried in the nebula's heart, a stellar engine so hidden it took decades to uncover. Most planetary nebulas are powered by a single dying star, but ERAS 16342-3814 plays by different rules. Deep within its dusty shroud, astronomers suspect a binary system locked in a gravitational tug-of-war. As one star sheds its outer layers, its companion, likely a compact white dwarf or neutron star, intercepts the material, funneling it into those narrow, high-velocity jets. Think of it like a cosmic pressure washer, with the companion star's gravity acting as the nozzle, concentrating the outflow into beams intense enough to punch through the surrounding gas. But the water mazes are more than just spectacular light shows. They're tracers mapping the otherwise invisible forces shaping the nebula. Each flicker in their microwave glow reveals shock waves rippling through the jets, while Doppler shifts in their light betray the twists and turns of their serpentine path. These details suggest the jets aren't firing steadily, they're pulsing, erupting in fits and starts as the binary stars dance ever closer. Some sections even show evidence of precession, wobbling like a spinning top, a telltale sign of the star's orbital motion imprinted on the outflows. What's even wilder is the chemistry. Water molecules shouldn't survive such extreme conditions, yet here they thrive, their spectral signatures glowing bright against the nebula's dusty backdrop. The secret: shielding. Dense clumps of dust act like bunkers, protecting the water from the star's ultraviolet wrath long enough for it to form intricate clusters. These same mazes have been spotted in other nebulas, but none with the velocity or clarity of the water fountain, making it a Rosetta Stone for understanding how molecules, and maybe even the precursors to life, can endure the violence of stellar death. The final irony: this nebula's fury is temporary. In a few thousand years, the central stars will exhaust their duel, the jets will fade, and the water mazes will dissipate into the void. But for now, the Water Fountain Nebula offers a rare glimpse into the chaotic physics of dying stars, proving that even something as familiar as water can become extraordinary when the universe turns up the pressure. Glowing like a sapphire lost in the cosmic deep, the Blue Snowball Nebula NGC 7662 presents a deceptively tranquil face to the universe. At first glance, its smooth, spherical shell radiates an almost ethereal blue, so pristine it could be mistaken for a celestial marble. But beneath that serene facade lies a storm of unimaginable violence, where gases scream outward at speeds exceeding 20 kilometers per second, and temperatures soar past 100,000 degrees. This isn't just a dying star's farewell, it's a raging inferno wrapped in the universe's most mesmerizing disguise, the secret to that hypnotic blue hue. Ionized oxygen atoms stripped of their electrons by the blistering ultraviolet radiation of the nebula's central star. As these charged particles recapture electrons, they emit light at specific wavelengths, in this case, a vivid aquamarine that dominates the nebula's glow. It's the same phenomenon that makes Earth's auroras dance with green, but on a scale so vast the entire structure could swallow our solar system whole. Yet what's fascinating isn't just the color, but its uneven distribution. Hubble's close-ups reveal subtle gradients, deeper blues near the core fading to turquoise at the edges, a telltale sign of the star's radiation weakening as it penetrates further into the nebula's shroud. But don't let that gentle gradient fool you. The blue snowball's interior is anything but orderly. High-resolution imagery exposes a labyrinth of knots and filaments, tangled like cosmic spaghetti by shockwaves rippling through the ejected gas. Some regions show bizarre, comet-shaped globules, dense pockets of material resisting the stellar wind's relentless push. These knots, each larger than our solar system, are thought to be the remnants of the star's outer layers, clumping together as they fled the dying core. And then there's the central star itself, a white dwarf so hot it emits most of its light in the invisible ultraviolet spectrum, its radiation ionizing the surrounding nebula into that famous glow. The real surprise, though, lies in the nebula's asymmetry. Despite its spherical nickname, the blue snowball isn't perfectly round. Its outer shell stretches slightly at the poles, hinting at a history of turbulence, perhaps a binary companion's gravitational influence or a magnetic field warping the outflow. Even more intriguing are the faint, fast-moving jets detected along its axis, invisible in optical light but screaming their presence in radio wavelengths. These jets, likely powered by the white dwarf's spin, suggest the nebula's calm exterior masks a dynamic engine still churning at its heart. What makes NGC 7662 truly remarkable isn't just its beauty or its hidden chaos, it's the contrast between the two. Like a whirlpool frozen in glass, the nebula captures a moment of celestial violence suspended in time, its turmoil disguised beneath a cloak of tranquil blue. It's a reminder that in space, even the most serene sights often have the fiercest hearts. The Egg Nebula isn't just hiding its secrets, it's wrapped them in layers of cosmic insulation so thick even visible light can't penetrate. Officially known as CRL2688, this enigmatic structure appears as little more than a faint smudge through optical telescopes. But switch to infrared and the veil lifts, revealing a breathtaking spectacle. Concentric rings of dust stacked like the layers of an onion, each one a frozen record of the central star's death throes. What makes these shells so extraordinary isn't just their precision, it's the story they tell about a star that refused to die quietly. Infrared imaging strips away the obscuring dust, exposing intricate details invisible to other wavelengths. The Egg Nebula's rings aren't smooth or uniform, they're rippled with instability, their edges frayed by shock waves and stellar winds. Each shell represents a pulse, a violent expulsion of material from the dying star, occurring roughly every few hundred years. Picture a clockwork eruption where the star convulses and coughs out another layer of carbon-rich dust, only to repeat the process again and again. But here's the twist, these eruptions aren't random. They're rhythmic, almost as if the star's interior is resonating like a giant bell, its vibrations triggering each new outburst. At the heart of this dusty labyrinth lies the star itself, a post-asymptotic giant branch star, caught in the brief but turbulent transition between red giant and white dwarf. Shrouded so completely that not even infrared can pierce its inner sanctum, this star is furiously heating up, its radiation pressuring the surrounding dust into those iconic concentric shells. Yet the real magic happens in the shadows. Twin jets of material, detected only in polarized light, blast outward perpendicular to the rings, carving bipolar cavities in the dust. These jets suggest the presence of a hidden companion, a smaller star or substellar object tugging on the dying star's ejector. shaping it into this intricate matryoshka doll of cosmic debris. What's even more fascinating is the dust itself. Unlike the fine, powdery grains found in most nebulas, the egg's dust is coarse and clumpy, rich with complex carbon molecules. These aren't just byproducts of stellar death, they're the building blocks of future worlds. Under the relentless barrage of ultraviolet light from the central star, these molecules are being broken apart and reassembled into ever more complex structures, some of which might even resemble the organic compounds that seeded life on Earth. The Egg Nebula's greatest lesson might be one of perspective. What looks like a dim, featureless blob to the naked eye transforms under infrared into a time-lapse of stellar evolution. Each ring a chapter, each jet a footnote in the autobiography of a dying star. And somewhere in those layered shadows, the universe is quietly assembling the ingredients for whatever comes next. The Medusa Nebula doesn't just borrow its name from myth, it fully earns it. Officially catalogued as Able 21, this sprawling cloud of gas stretches 4 light-years across, its long, sinuous filaments writhing like the serpentine hair of its namesake monster. But unlike the ancient Gorgon, these glowing tendrils aren't petrifying anyone, they're revealing the violent forces rippling through space as a dying star exhales its final breath. What makes these filaments so mesmerizing isn't just their eerie resemblance to snakes. It's the fact that each one is a fossilized shockwave, a frozen echo of the star's death throws echoing across millennia. At the heart of this cosmic spectacle lies a white dwarf, the smoldering remnant of a sun-like star that shed its outer layers roughly 9,000 years ago. But this wasn't a gentle shedding, it was a supersonic explosion. As the star's core collapsed, it unleashed a torrent of stellar wind, a stream of charged particles racing outward at speeds topping 150 kilometers per second. When this wind slammed into the slower-moving gas ejected earlier, it created titanic shock fronts, compressing and heating the material until it glowed in vivid shades of green and red. Those glowing ribbons, they're the scars of those collisions, etched into space like brushstrokes on a cosmic canvas. Hubble's observations reveal even wilder details. The filaments aren't just random squiggles, they're braided, with some strands twisting around each other like DNA helices. This intricate structure hints at magnetic fields channeling the outflow, or perhaps turbulence in the stellar wind itself, knotting the gas as it expands. And then there's the color. The dominant green hue comes from doubly ionized oxygen, a telltale sign of the gas being heated to extreme temperatures. Meanwhile, the fainter red regions, rich in hydrogen, mark cooler pockets where the shocks haven't fully penetrated. It's a thermal map of chaos painted across the void. But the real surprise lies in the nebula's asymmetry. Unlike the butterfly or the ring, the Medusa's filaments sprawl unevenly, with some tendrils stretching twice as far as others. Astronomers suspect this lopsidedness traces back to the star's final moments, maybe a last convulsive ejection hurled more material in one direction, or a companion star's gravity tugged the outflow off kilter. Whatever the cause, the result is a nebula that feels alive, its gaseous snake still slithering outward, carrying the star's legacy into the darkness. The Medusa Nebula isn't just a relic of destruction, it's a time capsule. Locked within those glowing strands are clues about how stars like ours recycle their ingredients back into the galaxy. Every filament is laced with carbon, nitrogen, and oxygen elements forged in the star's core and now destined to become part of future worlds. So while its name may evoke myth, the Medusa's true story is one of transformation, proving that even in death, stars don't just vanish. They rewrite the universe. The Calabash Nebula doesn't just transition from red giant to planetary nebula, it erupts in a cosmic tantrum so violent, astronomers nicknamed it the Smashing Pumpkin. Officially catalogued as OH2 31.8 plus 4.2, this celestial spectacle is anything but serene. Instead of gently shedding its outer layers, the dying star at its core is essentially detonating, hurling gas and dust outward at speeds exceeding 700,000 kilometers per hour. That's fast enough to cross the continental United States in less than 2 seconds. The result, a nebula that looks less like a delicate cosmic bubble and more like a stellar car crash frozen in time. What makes the calabash truly unique is its sheer turbulence. Most planetary nebulas form when aging stars release their outer layers in relatively controlled bursts, creating smooth, symmetrical shapes. But here, the star's death throes resemble a cosmic food fight. As the red giant's core collapses, it ejects material in opposing jets, blasting through slower-moving gas like shotgun pellets through tissue paper. This collision creates shockwaves so powerful they heat the surrounding gas to millions of degrees, lighting it up in X-rays. The nebula's fragmented, clumpy structure, its pumpkin resemblance, comes from these violent interactions, with dense knots of gas surviving the chaos like boulders in a hurricane. Then there's the chemistry. The calabash's outer layers are rich in sulfur and nitrogen, elements forged deep in the star's core and now being flung into space. These molecules shouldn't survive such extreme conditions, yet here they are, clinging to existence in the nebula's turbulent wake. Radio telescopes have even detected unusual compounds like silicon monoxide, a molecule typically found in the gritty disks around young stars, not the wreckage of dying ones. This suggests the calabash's destruction is also an act of creation, forging materials that might one day seed new planetary systems, but the wildest detail. The nebula's central star isn't done yet. Observations reveal it's still convulsing, its winds accelerating as it inches closer to becoming a full-fledged planetary nebula. In a few thousand years, the calabash's chaotic shroud will dissipate, leaving behind a white dwarf surrounded by glowing gas, a phoenix rising from the stellar wreckage. For now, though, it's a rare front-row seat to stellar death in action, proving that even in the cosmos, there's more than one way for a star to bow out. Some fade quietly, others go out with a bang, or in this case, a smash. The Saturn Nebula doesn't just share a name with the ringed planet, it mimics its celestial majesty with an eerie precision. Catalogued as NGC 7009, this planetary nebula boasts a pair of enigmatic polar bulges that extend outward like cosmic handles, giving it the appearance of Saturn suspended among the stars. But these aren't gentle curves sculpted by gravity. They're the scorched aftermath of a stellar windstorm, where gales of charged particles race from the central star at speeds topping 1,000 kilometers per second, fast enough to circle Earth's equator in under a minute. What creates such bizarre symmetry in the chaos of stellar death? The answer lies in the white dwarf at the nebula's heart, a remnant so hot it burns at nearly 55,000 degrees Celsius. As the dying star shed its outer layers, it didn't just exhale evenly into space. Instead, its equator became clogged with denser material, slowing the outflow there, while the poles remained clear, allowing radiation and winds to blast through unimpeded. The result, two opposing jets of superheated gas, punching through the slower-moving equatorial ring like torches through tissue paper. Over millennia, these jets carved the nebula's iconic polar bulges, shaping them into the delicate loops we see today. Hubble's razor-sharp vision reveals even wilder details. The bulges aren't smooth, they're ribbed with concentric shells like tree rings marking the star's periodic outbursts. Each ridge represents a pulse of material ejected at slightly different speeds, creating shock waves that ripple through the surrounding gas. Even more intriguing are the faint, finger-like protrusions at the tips of each bulge, likely formed when denser clumps of gas resisted the wind's push, leaving behind trails like cosmic fingerprints. But the real showstopper is the central star's invisible handiwork. Spectroscopic studies reveal the nebula's innermost regions are laced with neon and oxygen elements forged under extreme temperatures in the star's final days. These heavy atoms act like cosmic breadcrumbs, tracing the paths of those hypersonic winds as they sculpted the nebula from the inside out. It's a reminder that even in death, stars don't just fade away, they engineer their own monuments atom by atom. The Saturn Nebula's beauty isn't just skin deep. Those polar bulges are more than ornamental. They're time capsules preserving the physics of stellar demise in glowing detail. By studying their structure, astronomers can decode not just how this star died, but how countless others will, including our own sun, billions of years from now. The universe has a flair for turning destruction into art, and NGC 7009 is one of its most exquisite masterpieces. The Ant Nebula doesn't just earn its nickname, it flaunts it with cosmic flair. Officially known as MZ3, this celestial wonder splits down the middle like a cosmic insect, its two glowing lobes stretching outward in near-perfect symmetry. But this isn't some quiet stellar exhale. It's a full-blown tantrum with gas screaming away from the central star at speeds approaching 1,000 kilometers per second. What could possibly sculpt a nebula into such a precise, insectoid shape? The answer might lie in forces so extreme they bend our understanding of stellar death. At first glance, the Ant's bipolar structure suggests a binary star system, a pair of stellar dancers choreographing their final act together. As one star sheds its outer layers, the other's gravity could funnel the ejected material into twin jets, carving those iconic lobes. But here's the twist: no companion star has been definitively spotted. Instead, astronomers are staring down another possibility: magnetic fields of unimaginable strength. Imagine the dying star's magnetic lines acting like invisible rails, channeling charged particles into collimated beams with laser-like precision. These fields could be so intense they overpower even the chaos of stellar winds, forcing the nebula into its ant-like silhouette. Yet the Ant Nebula isn't just a case of stellar puppetry. Its lobes are layered with surprises. Hubble's close-ups reveal delicate filamentary structures within them, like veins in a leaf, evidence of shockwaves rippling through the gas. Near the center, a dense equatorial ring girds the star, likely leftover material that didn't escape the polar outflows. And then there's the star itself, a white dwarf so hot it ionizes the surrounding gas into a vivid green and red glow. But the real enigma is the lobe's composition. They're rich with nitrogen and oxygen, elements cooked in the star's core and now being hurled into the void. The most tantalizing detail: the ant's lobes aren't static. Observations suggest they're expanding at slightly different rates, hinting at asymmetrical forces at play. Some theorists propose the star's rotation is skewing the outflows, like a wobbly top spraying water unevenly. Others point to episodic eruptions, violent bursts of material ejected at different times, each leaving its mark on the nebula's shape. Whatever the cause, the Ant Nebula stands as a masterpiece of cosmic engineering, proving that even in death, stars can craft structures of eerie precision. One thing's certain: the Ant Nebula refuses to fit neatly into textbooks. Whether sculpted by hidden companions, mega-magnetic fields, or some yet unknown physics, its bipolar lobes challenge us to rethink how stars shape their final act. And with every new observation, this celestial insect reveals another layer of its mystery, a reminder that the universe's most dazzling performances often come with the strangest stage directions. The Stingray Nebula doesn't just stand out for its graceful, wing-like curves. It holds a cosmic record that rewrites our understanding of stellar life cycles. Officially catalogued as Hen 3-1357, this celestial wonder is the youngest known planetary nebula, caught in the act of emerging from its dying star. When astronomers first spotted it in the 1980s, it was barely distinguishable from an ordinary red giant. Fast forward a few decades, and it's transformed into a glowing, ionized bubble, its central star heating up so rapidly it's like watching a cosmic time-lapse in real time. What makes the Stingray so extraordinary is the speed of its metamorphosis. Most planetary nebulas take millennia to form, their central stars gradually shedding layers as they transition into white dwarfs. But the Stingray's central star has surged in temperature from around 20,000 degrees Celsius to over 50,000 in just 40 years, a blink of an eye in stellar terms. That intense ultraviolet radiation has ignited its expelled gas, causing the nebula to fluoresce in vivid blues and greens, like a neon sign flickering to life in the void. Hubble's snapshots reveal even wilder details. The nebula's delicate tendrils, resembling the fins of its namesake ray, aren't static. They're racing outward at nearly 20 kilometers per second, propelled by the star's furious winds. Meanwhile, the inner shell glows doubly bright, a sign of heavier elements like oxygen and nitrogen being forged in the star's death throes and flung into space. But the real shocker, the Stingray might not be done evolving. Some models suggest it could fade within the next century, its gas dispersing too quickly to sustain its glow, making it a fleeting masterpiece in the cosmic gallery. What's haunting is how much this rapid transformation mirrors our own sun's future. When it exhausts its fuel billions of years from now, it too will swell, shed its layers, and for a brief, brilliant moment illuminate its own planetary nebula. The Stingray offers a rare front-row seat to that process, compressed into a human timescale. It's a reminder that even in the vastness of space, some stars burn bright and fast, leaving behind beauty as ephemeral as it is breathtaking. Staring out from the depths of Ursa Major, the Owl Nebula gazes back with twin voids so unsettlingly symmetrical they seem almost deliberate. Officially catalogued as M97, this planetary nebula earned its nickname from the two dark patches that pierce its glowing shell like hollow, unblinking eyes, a celestial face etched into the fabric of space. But these aren't mere coincidences of gas and shadow. They're the handiwork of stellar winds, gusts of charged particles screaming from the nebula's central white dwarf at speeds that could cross the continental United States in seconds. Over millennia, these winds have sculpted the nebula's outer layers, carving cavities so precise they give the illusion of something watching from the void. Amateur astronomers first noted the owl's haunting visage in the 19th century, sketching its eerie countenance through modest telescopes. Even today, under dark skies, backyard observers can spot those vacant eyes, a testament to how strikingly human our brains interpret cosmic patterns. But modern instruments reveal the truth behind the illusion. The eyes are actually low-density regions where the central star's radiation has blasted through thinner portions of the nebula's shell, leaving behind gaps that absorb rather than emit light. Surrounding them, the nebula's brighter regions glow predominantly green, a signature of ionized oxygen excited by the white dwarf's ultraviolet fury. What's fascinating is how the owl's structure defies expectations. Most planetary nebulas with bipolar features, like the Butterfly or Ant nebulas, showcase symmetrical lobes ejected along an axis. But M97's eyes aren't lobes. They're absences, negative spaces where the nebula's material has been excavated rather than added. Some theories suggest magnetic fields funneled the dying star's winds into concentrated beams, drilling those voids like cosmic sandblasters. Others point to a binary companion's gravitational influence, though no second star has been definitively spotted. Then there's the nebula's texture. Hubble's close-ups expose delicate filamentary structures woven throughout its shell, resembling the fine threads of lace. These filaments, rich in hydrogen and nitrogen, are thought to be remnants of the star's outer layers, shredded by turbulence as they expanded into space. The overall effect is a celestial owl with feathers of ionized gas, its plumage ruffled by stellar winds. But perhaps the most haunting detail is the nebula's age. At roughly 8,000 years old, the owl is middle-aged for a planetary nebula, its glow already fading as the gas disperses into the interstellar medium. In another few millennia, those iconic eyes will dissolve completely, leaving no trace of their watchful gaze. For now, though, M97 remains a cosmic Rorschach test, a reminder that even in the cold vacuum of space, we can't help but see the faces of our myths staring back at us. The lemon-sliced nebula gleams in the cosmos like a drop of citrus suspended in the dark, its near-perfect spherical glow defying the chaos typical of stellar death. Officially catalogued as IC3568, this planetary nebula stands out not for intricate loops or violent jets, but for its deceptively simple structure, a luminous orb so uniform it could pass for a cosmic Christmas ornament. While most nebulas twist into asymmetrical spirals or jagged fragments, the lemon slice floats serenely, its symmetry so precise it challenges our assumptions about how stars expire. What crafts such a flawless sphere? The answer lies in its star's unusually tranquil demise. Unlike the fiery tantrums of the calabash or the binary theatrics of the Necklace Nebula, IC3568's progenitor exhaled its outer layers in a slow, steady stream, like a balloon deflating evenly in zero gravity. Without companion stars to tug the ejector off course or magnetic fields to warp its expansion, the gas drifted outward in all directions at once, forming this rare, textbook-perfect bubble. Hubble's ultraviolet observations reveal the secret behind its signature glow. Ionized helium and oxygen, lit up like a neon sign by the central white dwarf's relentless radiation. But don't mistake simplicity for monotony. Zoom in, and the lemon slice's subtle textures emerge. The nebula's edges ripple with faint concentric waves, fossilized echoes of the star's final pulsations, each one a thermal heartbeat recorded in gas. Near the core, the glow intensifies to a searing blue-white, betraying the white dwarf's staggering surface temperature of nearly 40,000 degrees Celsius. Yet the real marvel is the nebula's transparency. Unlike the egg nebula's dusty shrouds or the bat shadow's opaque disks, IC3568 is so optically thin, astronomers can peer straight through its outer layers, studying the dying star's exposed core with rare clarity. This transparency unlocks a cosmic time capsule. Spectroscopy reveals the lemon slice is rich with carbon and nitrogen, elements forged in the star's core and now being recycled into the galaxy. These aren't just ashes, they're seeds destined to one day be incorporated into new stars, planets, or even the building blocks of life. The nebula's spherical shell acts like a greenhouse for molecule formation, its gentle expansion allowing compounds to assemble without being shredded by turbulence. The lemon slice's greatest lesson might be its rarity. In a universe where stellar death is often violent and asymmetrical, it's a serene outlier, proof that some stars bow out with quiet dignity. Yet even here, mysteries linger. Why did this star avoid the magnetic storms or binary disruptions that twist most nebulas into knots? Was it simply born under calmer conditions, or did it somehow shed its layers before chaos could take hold? For astronomers, IC3568 is both a benchmark and a puzzle, the universe's closest approximation to a perfect sphere, and a reminder that even in simplicity, the cosmos keeps secrets. The ghost of Jupiter Nebula doesn't just borrow its name from the solar system's largest planet. It pulls off such a convincing cosmic impersonation that early astronomers often mistook it for Jupiter itself when peering through small telescopes. Officially catalogued as NGC 3242, this planetary nebula glows with a pale, bluish-green disk so eerily similar to Jupiter's atmospheric bands that it even fools the eye at similar magnifications. But zoom in, and the illusion shatters, revealing a structure far more complex than any gas giant, concentric shells of gas layered like an onion, each one a preserved moment in the dying star's final violent acts. What makes this nebula's mimicry so uncanny isn't just its color or apparent size, it's the dynamics of its glow. Under low magnification, the nebula's brightest inner region appears smooth and uniform, much like Jupiter's cloud tops. But Hubble's sharp gaze exposes the truth, a frenetic inner bubble of gas expanding at nearly 20 kilometers per second, collides with slower-moving material ejected millennia earlier. This collision creates shock waves that excite the gas, causing it to fluoresce in those iconic hues. Meanwhile, the outer shells, faint but detectable in long-exposure images, stretch nearly 2 light-years across evidence of the star's earlier, slower eruptions. The real marvel lies in the nebula's chemistry. Unlike Jupiter's hydrogen-helium atmosphere, the ghost's spectral signature reveals a cocktail of ionized oxygen, nitrogen, and hydrogen, each element glowing at specific wavelengths under the ultraviolet assault of the central white dwarf. This star, now a searing remnant hotter than 60,000 degrees Celsius, bombards the surrounding gas with radiation, stripping electrons from atoms and forcing them to emit light as they recapture them. The result, a celestial chameleon, mirroring a planet's visage while hiding the turmoil of stellar death beneath its serene facade. Yet the ghost of Jupiter's most haunting feature isn't its appearance, it's its asymmetry. Despite its spherical nickname, the nebula's outer shells warp slightly at the poles, betraying the presence of a bipolar outflow. Some astronomers suspect a companion star's gravitational pull tugged the ejector off kilter, while others propose magnetic fields shape the chaos into these subtle deviations. Whatever the cause, this distortion serves as a reminder. Even the most polished cosmic illusions are born from violence. And then there's the central star itself, a white dwarf so fiercely luminous it outshines our sun by a factor of 1,000 despite being smaller than Earth. This remnant doesn't just light up the nebula, it's actively sculpting it, with stellar winds carving cavities into the surrounding gas like an invisible knife. Spectroscopic studies reveal the star's surface is laced with heavy metals, elements that should have sunk into its core under gravity's pull. Their presence suggests the white dwarf is still convulsing, its atmosphere roiling with material dredged up from the depths. The ghost of Jupiter may be a master of disguise, but its greatest trick is how it challenges our expectations. What looks like a tranquil planetary doppelganger is, in reality, a time lapse of stellar demise, a layered chronicle of eruptions, shocks, and radiation, all preserved in glowing gas. It's a reminder that the universe loves a good costume, but the truth behind the mask is always far more fascinating. The Spirograph Nebula doesn't just dazzle, it hypnotizes, its concentric rings swirling with a precision so exact, it looks like the universe dipped a cosmic pen in stardust and traced perfect geometric patterns across the void. Officially catalogued as IC418, this planetary nebula earns its nickname from the uncanny resemblance to the intricate designs created by a spirograph toy, those looping, interlaced curves that seem too perfect to occur naturally. Yet here they are, etched into the fabric of space by the rhythmic death throes of a star that refused to fade quietly. What crafts such mathematical elegance from stellar chaos? The secret lies in the central star's heartbeat like pulsations. As the star shed its outer layers, it didn't eject them in a steady stream or a single violent burst. Instead, it pulsed, expanding and contracting at regular intervals, each convulsion launching another shell of gas into space at slightly different speeds. Imagine a musician blowing into a trumpet, their breath coming in controlled bursts, each note shaping the air into visible sound waves. Now replace the trumpet with a dying star and the sound waves with rippling spheres of ionized gas, and you've got the Spirograph Nebula's mesmerizing structure. Hubble's close-ups reveal the layers in staggering detail. Each ring is a fossilized echo of one of those pulsations, a snapshot of the star's final millennia compressed into glowing bands. But here's the twist: these rings aren't static. They're expanding, their delicate curves warped by the push and pull of the central star's radiation pressure. Near the core, the rings glow blue-green, heated to searing temperatures by the white dwarf's ultraviolet fury. Farther out, they fade into reddish hues where nitrogen and hydrogen emit softer light as they cool in the depths of space. The real marvel is the nebula's symmetry. Unlike the Butterfly or the Ant Nebula, where jets and magnetic fields twist the gas into asymmetrical shapes, IC 418's pattern is almost flawlessly circular. This suggests the star's pulsations were remarkably uniform, its death spasms free from the gravitational tug of companion stars or the distorting grip of strong magnetic fields. It's a rarity in stellar demise, a quiet, rhythmic unraveling that left behind a masterpiece of natural geometry. Yet the spirograph's beauty isn't just skin deep. Hidden in those glowing rings are clues about the star's composition. Spectroscopy reveals streaks of carbon and oxygen, elements forged in the star's core and now being recycled into the cosmos. These aren't just pretty patterns, they're the raw ingredients for future stars, planets, and perhaps even life. The Spirograph Nebula, then, isn't just art, it's alchemy, turning the remnants of a dead star into the building blocks of tomorrow. And there's one final, haunting detail. The central white dwarf, though small and faint, is far from dormant. Observations suggest it's still pulsing subtly, its brightness flickering like a candle in the cosmic wind. These faint variations hint at ongoing instability, as if the star hasn't quite settled into its afterlife. It's a reminder that even in death, stars can keep surprising us, their legacies written not just in static gas, but in the slow, silent rhythms of the universe. Don't let the name fool you. The Little Dumbbell Nebula is anything but simple. Catalogued as M76, this cosmic spectacle might sound like a modest cousin to the famous Dumbbell Nebula, but its structure tells a far more dramatic story. What appears as a faint, symmetrical hourglass through amateur telescopes unravels under Hubble's gaze into a turbulent ballet of stellar death, with two luminous lobes racing away from each other at breakneck speeds. This isn't just another planetary nebula, it's a textbook example of bipolar chaos where a dying star's last gasp split the cosmos in two. The secret to M76's dual-lobed shape lies in its explosive origins. Roughly 10,000 years ago, the central star, once similar to our Sun, began shedding its outer layers in fits and starts. But unlike the serene exhale of the lemon-sliced nebula, this star's demise was anything but orderly. Astronomers suspect a hidden companion star or a ferocious magnetic field funneled the ejected material into two opposing jets, carving out the nebula's signature lobes like cosmic ice cream scoops. The result, a structure that looks deceptively delicate from afar but reveals its violence up close, with shockwaves rippling through the gas like sonic booms frozen in time. What's especially fascinating is how those lobes glow. The brighter inner regions shine with the telltale green of ionized oxygen, heated to searing temperatures by the ultraviolet radiation of the exposed stellar core. Meanwhile, the fainter outer tendrils glow red with hydrogen, remnants of earlier ejections now cooling in the depths of space. This layered coloration acts like a cosmic timekeeper, each hue marking a different chapter in the star's death throes. But here's the twist: M76 isn't just a relic. At its heart lies a white dwarf so hot it burns blue-white, its radiation still sculpting the surrounding gas. Recent observations even hint at a faint outer halo, a ghostly shell of material ejected tens of thousands of years earlier, now illuminated by the central star's glare. It's a reminder that planetary nebulas aren't static snapshots, they're dynamic works in progress, evolving long after their stars have faded. The Little Dumbbell's greatest irony might be its name. Far from a simple cosmic weight, it's a masterpiece of stellar engineering, where gravity, magnetism, and radiation conspired to create a structure of eerie symmetry from utter chaos. And for astronomers, it's a golden opportunity, a nearby laboratory to study how stars like ours might one day leave their mark on the galaxy. We've marveled at the etched hourglass nebula's symmetry before, but there's another layer to its precision, one written in the invisible ink of magnetism. Mycen 18's razor-sharp jets and flawless hourglass shape might owe their surgical accuracy to an unseen cosmic force. a magnetic field so finely tuned it acts like a sculptor's chisel on the chaos of stellar death. Recent observations reveal something extraordinary. The nebula's polar outflows aren't just flowing. They're following an intricate roadmap of magnetic field lines as if guided by some celestial GPS. These fields don't just nudge the gas gently, they whip it into shape. Spectroscopy shows the ionized gas streaming from the nebula's poles is split into finely collimated beams, each one narrower than our solar system. That kind of focus is unheard of in most planetary nebulas, where outflows typically fan out like water from a hose. But here, the gas moves with laser-like precision, suggesting the magnetic fields aren't just present, they're dominant, overpowering the star's turbulent winds to carve those iconic hourglass walls. The real breakthrough came when astronomers mapped the polarization of light around the central star. By studying how dust grains align with magnetic fields, they uncovered a hidden architecture, vast, looping field lines running parallel to the jets like railroad tracks for charged particles. These fields likely originated in the star's interior during its death throes, amplified as the collapsing core spun faster and faster, a cosmic dynamo turning chaos into order. Now here's the twist. The same data revealed another surprise. The polar outflows aren't identical. The southern jet shows subtle kinks and bends, while the northern one remains arrow straight. Some researchers think this asymmetry traces back to the star's final moments, when instabilities in its magnetic field caused one pole to erupt more violently than the other. Others suggest a stealthy companion star's gravity tugged at the jets off-center, warping their paths. Either way, these imperfections are clues, hinting that even the most precise cosmic structures are born from turbulence. The most tantalizing detail, those magnetic fields might be doing more than shaping the nebula, they could be fueling it. X-ray observations detect faint emission near the central star, a sign of particles being accelerated to near-light speeds along the field lines. It's as if the dying star left behind not just a glowing corpse, but a natural particle accelerator, one that's still crackling with energy millennia later. The etched hourglass magnetic mystery reminds us that beauty in space often has invisible scaffolding. What looks like a serene cosmic masterpiece is actually a battleground where magnetism and wind clash and somehow, against all odds, create perfection. The frosty Leo Nebula doesn't just shimmer in the cold void, it practically glitters, its dust grains encased in thick layers of ice like microscopic cosmic snowflakes. Officially catalogued as ERAS 09371+1212, this planetary nebula earned its frosty nickname for a reason. Its outer reaches are so rich in frozen water and other ices, they reflect starlight like a diamond-dusted windowpane. But this isn't just a celestial winter wonderland. The presence of these icy grains challenges everything we thought we knew about where and how water survives the violent death throes of stars. At first glance, ice shouldn't exist here at all. Planetary nebulas are born from stars like our Sun, which swell into red giants before shedding their outer layers in searing stellar winds. The intense ultraviolet radiation from the exposed core should obliterate any nearby ice, vaporizing it in seconds. Yet frosty Leo's ices endure, cloaking dust particles in a frigid armor. How? The answer lies in the nebula's unusual structure. Unlike most planetary nebulas which expand evenly, frosty Leo's outer shell is lumpy and fragmented, with dense pockets of gas shielding the ice from the star's lethal glare. Picture a snowbank tucked in the shadow of a boulder. Even in summer, some patches stay frozen. The real shock came when spectrometers identified not just water ice, but a cocktail of frozen molecules clinging to these dust grains: carbon monoxide, methane, and even complex organics like methanol. This icy menagerie suggests the nebula's outer regions are staggeringly cold, dipping below -260 degrees Celsius, just a whisper above absolute zero. These temperatures turn the nebula into a cosmic deep freezer, preserving ices that might otherwise vanish in the blaze of stellar death. But here's the twist: frosty Leo's ices aren't just passively surviving. They're active participants in the nebula's chemistry. As the central star's faint light filters through the icy dust, it triggers photochemical reactions, breaking molecules apart and reassembling them into new compounds. Some researchers believe this process could spawn prebiotic molecules, simple precursors to the building blocks of life. It's a notion that turns the nebula into more than a pretty cosmic frost. It's a potential factory for organic chemistry in the most unlikely of places. The implications ripple far beyond this single nebula. If ices can endure here, they might survive in countless others, hidden in the shadows of fragmented gas clouds. That means the water vapor we detect swirling around young stars, and eventually planets could have hitchhiked there aboard icy dust grains from dying stars like frosty Leo's progenitor. In a sense, this nebula's frozen cloak might be a delivery system, ferrying water and organics across the galaxy, one tiny, glittering speck at a time. What's haunting is how temporary this frosty phase will be. As the central star heats up, its radiation will slowly eat away at the ices, sublimating them into gas. Already, the inner regions of the nebula show signs of thawing, their spectral signatures shifting as molecules break free from their frozen cages. In a few thousand years, frosty Leo's winter will end, its diamonds of ice dissolving into the void. But for now, it stands as an icy time capsule, a fleeting reminder that even in the furnace of stellar death, the universe finds ways to keep its cool. The Cotton Candy Nebula floats through space like a confectionery daydream, its delicate filaments so wispy and ethereal they seem barely tethered to reality. Officially known as ERAS 17150-3224, this planetary nebula defies the usual billowing clouds or jagged shockwaves of its kin instead. Its structure resembles spun sugar, with gauzy tendrils stretching outward in a celestial web so fragile, a gust of stellar wind might tear it apart. Yet these filaments aren't just cosmic decoration, they're the fingerprints of turbulence, a record of chaos frozen in gas and dust. What weaves a nebula into such intricate threads? The answer lies in the physics of instability. As the dying star at the nebula's core ejected its outer layers, the material didn't flow smoothly into space. Instead, it collided with itself like rivers of gas crashing into invisible boulders. These collisions triggered turbulence, eddies, and whirlpools on a scale so vast they could swallow solar systems whole. The result, a cascade of ripples, each one shearing the gas into finer and finer strands, until the entire nebula became a labyrinth of luminous filaments. But here's the twist: turbulence alone doesn't explain the cotton candy's ghostly persistence. Most turbulent structures dissipate quickly, their energy bleeding away into the void. Yet these filaments endure, their delicate balance maintained by an unlikely force radiation pressure from the central star. As ultraviolet light streams outward, it pushes against the gas, stretching the filaments even thinner while preventing them from collapsing or dispersing. It's a cosmic tug-of-war where chaos and order reach an uneasy truce, producing a nebula that looks as if it's woven from starlight itself. Hubble's close-ups reveal even stranger details. The filaments aren't uniform. Some glow brighter, their cores dense with molecules like hydrogen cyanide and silicon monoxide, while others fade into near transparency. This patchwork suggests the star didn't die in one steady exhale, but in fits and starts, with each pulse of material encountering different conditions in its surroundings. Some regions may have been denser, slowing the gas and allowing it to clump, while others were near vacuum, letting the filaments spread unimpeded. The Cotton Candy Nebula's greatest lesson might be its fragility. Unlike the sculpted jets of the Twin Jet Nebula or the magnetic precision of the etched hourglass, this structure feels ephemeral, a momentary artwork destined to dissolve. Already, its outer tendrils are fading, their material dispersing into the interstellar medium. Yet even in its evanescence, it offers a glimpse into the universe's quieter creative processes. Not all stellar deaths are violent explosions or magnetic spectacles. Some are whispers, their beauty lying in the subtle interplay of turbulence and light, a reminder that destruction can sometimes be as delicate as lace. Most stars fade quietly into white dwarf oblivion, but Sakurai's object staged the ultimate cosmic comeback. This celestial rebel didn't just refuse to die, it resurrected itself, exploding back to life decades after its funeral shroud of gas had already formed. Nestled within a fading planetary nebula in Sagittarius, this white dwarf shocked astronomers in the 1990s when it suddenly flared thousands of times brighter, rekindling nuclear fusion in an event so rare it's been witnessed only a handful of times in history. The born-again phenomenon isn't just a second act, it's a stellar revolution rewriting the rules of how stars die. What triggers such a dramatic rebirth? The answer lies in a last-minute helium heist. As Sakurai's object cooled into a white dwarf, residual helium in its outer layers reached critical pressure and temperature, then detonated in a runaway thermonuclear reaction. Imagine pouring gasoline on dying embers. The dormant star's outer shell violently reignited, swelling back to red giant proportions in mere years. Hubble's observations captured the aftermath, a blazing stellar phoenix, its resurrected surface now churning at over 20,000 degrees Celsius, surrounded by the very nebula it had ejected millennia earlier. The nebula itself became a time traveler. Already thousands of years old when the star reignited, its delicate shells of gas suddenly found themselves bathed in intense new radiation. The shockwave from the reborn star plowed into these ancient ejecta, lighting up complex structures previously invisible. Infrared images reveal bizarre, comet-shaped knots within the nebula, dense pockets of material sculpted by the newborn stellar winds, their tails streaming away like cosmic weather vanes. Even more astonishing, the nebula's chemistry shifted. Spectra show carbon-rich dust forming in real time as the star's renewed fury forged heavy elements and spewed them into its aging shroud. Yet the most haunting detail is the timeline. While most stellar processes unfold over millennia, Sakurai's object transformed at breakneck speed. Between 1996 and 2000, its surface temperature skyrocketed by nearly 30,000 degrees, an evolutionary leap that should have taken millions of years. This hyper-speed metamorphosis left astronomers scrambling, as textbooks had no framework for changes this abrupt. The nebula responded in kind, its outer layers fluorescing in new hues as ultraviolet radiation penetrated deeper, exposing previously hidden filaments that twisted like stirred cream. Now the star's second life is waning. Recent observations show it's contracting back toward white dwarf status, its outer layers dissipating into space once more. But its legacy lingers in the nebula's altered chemistry, a double-layered relic of two distinct deaths. For scientists, Sakurai's object is a Rosetta Stone, proving that stellar evolution isn't linear. Sometimes stars get a second chance to sculpt their own memorials, and in doing so, reveal how volatile the cosmos can be when dying embers decide to burn again. From the Butterfly Nebula's symmetrical wings sculpted by invisible magnetic forces to the Red Square Nebula's eerie geometric perfection, each of these 30 cosmic enigmas has rewritten the rules of stellar death. We've witnessed planetary nebulas that defy temperature extremes like the Boomerang, chilling space to near absolute zero, while the central stars of others burn hotter than small galaxies. We've explored structures that mirror mythological beasts, celestial jewelry, even frozen artwork, all carved by the chaotic interplay of gravity, radiation, and hidden companions. The Cotton Candy Nebula's delicate filaments and the Frosty Leo's glittering ice prove that destruction can birth breathtaking fragility, while Sakurai's object taught us that some stars refuse to die quietly, literally reigniting their own funerals. These nebulas aren't just pretty relics, they're cosmic laboratories. The water fountain's supersonic jets and the hand of God's magnetic fingers reveal physics pushed to extremes, while the etched hourglass and spirograph nebulas show how dying stars can become universe-scale artists. Even their chemistry astonishes, from the soccer ball molecules of TC1 to the organic rich ices of frosty Leo. They're proof that stars manufacture life's ingredients in their final breaths. Every discovery peels back another layer, exposing how much we've underestimated these stellar tombstones. Perhaps the greatest revelation is how planetary nebulas force us to rethink our place in the universe. The Helix Nebula mirrors our sun's fate, while the necklace's cannibal stars warn that even solar systems can turn predatory. They're not just distant curiosities, they're glimpses of Earth's eventual fate written in glowing gas. Now it's your turn. Which of these 30 shattered your expectations? Was it the Medusa's serpentine tendrils, the bat shadow's ghostly wings, or the lemon slice's impossible perfection? Drop your pick in the comments and let's keep unraveling these cosmic mysteries together. The universe's strangest wonders are always waiting, you just have to look up.